Alrighty guys, so in today's lecture we're going to be talking about a few atoms that are an exception to the octet rule. But before we do that, let's kind of review what the octet rule means. Basically, just to review, the octet rule means that atoms, when we draw their structures, they're going to want 8 valence electrons. Of course, the exception is going to be hydrogen, which wants 2 valence electrons. Okay, and so for example, if we had a molecule like CH4, we know that when we draw this structure, we're going to put C in the middle. So I'm going to put C in the middle. We put the H's on the outside. Okay, and what we're going to do is we're going to count up how many electrons they bring. So C is box number 1, 2, 3, 4. So since C is 4, C is going to contribute 4 valence electrons. Hydrogen is box number 1 in its row, so it's going to contribute 1. But since there's 4 of them, we're going to be adding 4. So it's going to be 4 plus 4. And so the 4 hydrogens contribute 4. So that means in this molecule, there are going to be 8 total valence electrons. Okay, so this is basically just review. And we just know that we need to make sure that everything is connected. And we know that our answer is correct if the H's have 2 valence electrons. So if we look, all of the H's have one line. One line equals to 2 valence electrons, so all the H's are good to go. And the octet rule tells us that every other atom other than H wants 8 valence electrons. And so carbon, if we count them up, there's 1, 2, 3, 4 lines. So there's 4 lines, and we know that each line is equal to 2 valence electrons. So we know that carbon has 8 valence electrons, which means that our answer is correct. And so that's basically the octet rule. You guys should be pretty familiar with it. It just means that all the atoms except hydrogen want 8. So carbon has 8, so that means carbon is good to go. So the reason why carbon only wants 2 valence electrons is actually very simple. If you notice, carbon is in the first row. Hydrogen. The reason why hydrogen wants 2 valence electrons is because it's on the first row. So if you remember the shell model, hydrogen only has one shell. And so hydrogen is pretty small, and that's why it can only hold 2 valence electrons. If it starts trying to get more shells or more electrons, what's going to happen is it's not going to be able to hold on to the electrons, and they're going to fly away. Now, just like how hydrogen can only hold 2 electrons because it's so small, there are some atoms that are big. And big atoms, they're going to be able to hold more than 8 valence electrons. It doesn't mean they have to, but they can. They have the potential to hold more than 8 valence electrons. And we're going to be talking about a couple of those exceptions. Okay, so you guys might want to write this down somewhere in your notes because it'll be very helpful today and as we go through this unit. There are going to be a couple elements that we're going to highlight that have the potential they can hold more than 8 valence electrons. Okay, so for example, P, phosphorus. Phosphorus is one of those interesting atoms that can hold more than 8 valence electrons. Phosphorus can hold 8 or 10. Okay, and these are just something that you're going to have to write down and memorize to have in the back of your repertoire when you're drawing these structures. Two other examples are sulfur and bromine. Now, if you notice, sulfur and bromine, they're going to be a little bit bigger, and so they can actually hold 8, 10, or 12. So phosphorus can hold 8 or 10. Sulfur and bromine can hold 8, 10, or 12. Okay, and there is another exception, but this one is less than 8. Boron, B, can hold 6 or 8. Okay, so those are just going to be some of the exceptions that you're going to have to know. Phosphorus has the potential to hold 8 or 10. Sulfur and bromine can hold 8, 10, or 12. Boron can hold 6 or 8. Now, I do want to mention one important thing. They can hold these bigger numbers. They don't have to hold that many. And so you shouldn't be taking away electrons from the other atoms. Remember, the octet rule still works. So if you're working with like carbon, nitrogen, oxygen, fluorine, silicon, chlorine, things like that, they're going to still want 8. They can hold more than 8, but they don't have to. Okay? All right, so let's do a quick example right here. We have PCl5. PCl5 is phosphorus and Cl5. So if we count up the electrons, what we're going to do is if we look at phosphorus, phosphorus is box number 1, 2, 3, 4, 5. That means phosphorus is going to bring 5 valence electrons to the table. If we look at chlorine, chlorine is box number 6, 7. Since chlorine is box number 7, it's going to contribute 7 valence electrons. But there are 5 chlorines. So that means we're going to have to multiply this by 5. That means we're going to have 35. So that means that the Cl's, they all contribute 35, and phosphorus contributes 5. Okay, so that means that gives us a grand total of 40 valence electrons in this structure. Okay, that means when we draw our picture, we need to have a total of 40 valence electrons. All right, so let's use the things that we know about our structures for covalent compounds to make our picture. So we know that one of the rules that we probably don't use as much as the other ones was rule number 3 is the electrons or the atoms that are more electronegative, they tend to be on the outside. Okay, so the more electronegative an atom is, the more on the outside that they want to be. Okay, so the two elements that we're working with here are phosphorus right here and chlorine. Okay, and so we know the one that is more electronegative wants to be on the outside. So if we remember our pattern for electronegativity is as you go up and as you go to the right, it becomes more electronegative. So if you notice, which one of these two is more electronegative? Hopefully you said chlorine is more electronegative, and the reason why is because it's more to the right. That's going to make it more electronegative. Since chlorine's more electronegative, it's going to want to be on the outside. So what we're going to do is we're going to put P somewhere in the middle, and then we're going to put the Cl's on the outside. Okay? All right, and we know that there has to be one connection between all the atoms. So what we're going to do is we're going to connect all the Cl's with the P's. So we're going to do something like that. Guess it looks like a star. We connect all of the Cl's to the P. Okay, so let's count up how many electrons we've used so far. So if I draw one line, that's 2, 4, 6, 8, 10. So I use 10. That means I have 30 electrons still left to use. Now we know that everything needs 8 valence electrons. So what we're going to do is we're going to make sure chlorine has 8 because of the octet rule. Octet rule means that atom wants 8, and so we're going to want to put electrons or make sure that chlorine has 8 electrons. Now you might be wondering, Mr. O, octet rule says that atoms only want 8, but if you look at phosphorus, how many valence electrons does phosphorus have? It has 1, 2, 3, 4, 5 lines. Since it has 5 lines, that means phosphorus right now has 10 valence electrons. Okay, but we said phosphorus is one of those interesting atoms that can hold 10. And so phosphorus is still good. You can leave phosphorus with 10 valence electrons. Okay, so phosphorus is good. All we need to do now is make sure that everything else, because of the octet rule, has 8. So chlorine needs to have 8. So let's start with this chlorine. It has 2, 4, 6, 8, 2, 4, 6, and then the line gives you 8. And you kind of get the pattern. You just need to put 6 valence electrons on all of the chlorines. Okay, so let's figure out how many valence electrons we used. Every chlorine we just added 6 in order to get them to 8. So 6, 12, 18, 24, 30. And so we used all 30. We used all 40 valence electrons. If you don't believe me, you can pause the video right now and count them all up. But we have 40 valence electrons. We have 8 on every single chlorine. And phosphorus has 10. But since it's one of the exceptions, it's good to go. All right, let's move on to another example. And this will be the last example for this video. Okay, we're going to do one that's a little bit trickier. This one is very ugly. It says H2SO4. All right, so if we start with H, H is the first box, so it's 1, but there's 2 of them, so there's going to be 2. If we look at S, S is box number 1, 2, 3, 4, 5, 6, so it's going to bring 6. And then oxygen is also box number 6, but there's 4 of them, so 4 times 6 is 24. So that means the total number of electrons here are going to be 32. Now, we know that H always goes on the outside, so I'm just going to put them, I guess, on the furthest parts, as far away from each other as they can be, so they can be on the outside. Okay, we know that oxygen is more electronegative, right? Because it's on the right and to the left. So that means oxygen is going to be more outside than the sulfur. So it looks like the sulfur is going to be somewhere in the middle. And what I'm going to do is I'm just going to put the oxygens around it just so we have them on the outside. Alright, so what we're going to do now is we're just going to make sure all of the atoms are connected. So what I'm going to do is I'm going to connect the oxygens with the sulfurs just so everything is connected. And we're also going to connect the hydrogens with the oxygens because hydrogens, again, they have to be on the outside. They can only make one connection. So everything is connected here. So what I'm going to do now is I'm just going to count up how many valence electrons we've used. We used 2, 4, 6, 8, 10, 12. So if we subtract 12 from 32, that means we have 20 valence electrons left to use. Now if we try to figure out which atoms are already happy, we know that hydrogen is happy because it has one line. So this hydrogen is happy, this hydrogen is happy, and if you look at sulfur, sulfur has 8. So we can kind of say sulfur is happy as well. Sulfur is happy because it has 8 valence electrons. Okay, that means the oxygens are unhappy, so we need to give them valence electrons until they get to 8. So what I'm going to do is I'm going to put 2 right here, 2, 4. Okay, so I used 4. That's going to get me to 16. I'm going to put 2, 4 here so that this oxygen also has 8. So that's going to give me 12. Okay, so let me circle these oxygens because these oxygens are happy. Okay, that means these oxygens are not happy. Okay, so what we're going to do now is we're going to add until they get to 8. So this oxygen has 2, 4, 6, 8. Okay, so I used 6 here, so that gets me to 6 valence electrons. And then we have another O here that requires 2, 4, 6. And that way it has 8. Okay, so it looks like everybody has 8 and the oxygens have 2, so this is it. This is going to be the structure of H2SO4. Now, we said sulfur can hold 8, 10, or 12, but here we don't need to have it hold 10 or 12. It only needs to have 8 in order to make everything happy. Okay? So, this is going to be the structure for H2SO4. Another way you could have drawn it, and this is just an option, is we could take these 2 electrons and we could have made a double bond here because sulfur now it has 2, 4, 6, 8, 10, and we could have also taken these 2 valence electrons and put a double bond here to make it 2, 4, 6, 8, 10, 12, and this sulfur would still be chilling because it has 12 valence electrons and we said sulfur can hold 12. And so this structure works as well. Just remember that there are multiple ways to do it. And so this structure will be fine because sulfur still has 12. You can draw it with 12 or with 8. Alright, so hopefully that was helpful, guys. Best of luck on your assignment. I'm on the Zoom call right now, so let me know if you guys have any questions, and we'll see you guys next time.